Okay, before we get into altering the sine and cosine functions, let's do a brief review of transformations of functions and how they work. So we have different operations that can be included in addition to the original function operation, whether it be sine or cosine. We can introduce addition or subtraction, and we can introduce multiplication or division. And which of those is introduced and where in the function it's introduced, that is, in relation to the original basic operation, does the addition occur after the basic operation or does it occur before the basic operation? These things can affect different transformations. So let's look at first addition or subtraction of a constant. In this case, the basic function operation occurs and then the addition of a constant happens afterward. That causes a vertical shift. What happens is that the function is evaluated like it normally would be, and the original output value is produced. And then we add to it, or subtract if it's negative. So what this literally does is it adds the value of k to every y value. Now, it's vertical shift because it occurs after the basic operation. So as I said, we produce the original output value and then make a change afterward. Over here, however, we have that minus h occurring before we get to the original function f. It's x minus h first before anything else. That addition or subtraction causes a horizontal shift. In this case, and if you recall, horizontal transformations tend to work kind of backwards or inverse from what's written. So the idea is that we have to take into account the change that's about to occur before we do anything. So we have to look at it and say, well, I know that I'm about to subtract something, so therefore I need to pick a bigger value to counteract it. And that causes us to have the kind of inverse relationship there. In this case, what we have to do is we have to solve x minus h equals 0. We take the inside expression, set it equal to 0, and the solution to that is the amount and direction of the horizontal shift. So what we do then is we're going to add that solution to each x value. And that will enact the shift on our function. Now, that takes care of addition or subtraction. The addition and subtraction cause shifts. Multiplication causes one of two things: a reflection and or a distortion, depending on the different values there. So this c times f of x, in this case we have, again, our function doing what it does and producing its output, and then we have a multiplication afterward. So that's going to affect the y-coordinate of every point. So this is a vertical reflection if c is negative, and it's going to cause a vertical distortion if C is anything other than positive or negative 1. Positive and negative 1, when multiplying, they don't really do much. The negative changes the sign of the output value. That would cause the reflection, but a positive 1 doesn't actually do anything because multiplying by 1 has no effect. But in any case, both of these things happen at the same time. You can do them in either order separately, but they do happen at the same time. All that ends up happening here is it multiplies every y value by C. So if C is negative 3, it will make every output value 3 times bigger and change its sign to negative. So it'll distort and reflect at the same time. That really only leaves one other thing for f of C times x. Like the horizontal shift, the multiplication by C is happening before the basic function operation. So this is going to cause us to have to choose an x value that takes that multiplication into account. What that means then is that, well, again, we can have trying to activate Siri there. We can have a horizontal reflection, again, if C is negative. We can also have a horizontal distortion, again, if C is anything other than a positive or negative 1. Now, what we get here, however, is that inverse kind of relationship, whereas in the vertical shift and the vertical reflection distortion, we do what it says. If it has plus k, we add k. If it has times c, we multiply by c. With the horizontal, it always has something of an inverse relationship. That's why f of x minus h, we end up adding the solution to each x value. And the idea is the way we'd get x by itself is add h to both sides. So we get a similar kind of situation here. In order to get x by itself, so to speak, we would end up having to divide by c. And that's exactly what happens to every x coordinate. So these are our 4 forms of the transformations, and these are the effects that each of them has on the ordered pairs of the function. So as long as we have a few ordered pairs of the function, and we can interpret the operations in the function, we can enact the transformations and get the new function, the transformed function. Of course, while we did establish the characteristics, the period and amplitude and midline and so forth of the sine and cosine function, we didn't nail down which points we need in particular. So let's move on and take a look at each of them and do exactly that. Actually, these points are referred to as the 5-point summary. There are 5 points that govern the cycle of the wave, whether it's sine or cosine. There are 5 points that govern the cycle of the wave. They are anytime the graph hits its midline, anytime it peaks or bottoms out. These 5 points of the sine function are your 5-point summary. if you have these 5 points and you can interpret the transformations, then you can make the new function. The 5-point summary is 0, 0, pi over 2 comma 1, pi comma 0, 3 pi over 2 comma negative 1, and 2 pi comma 0. Now, I suppose you can memorize those points, but like the unit circle, there's kind of a better way to handle it. The kind of neat thing is that these are just all the quadrant angles. So all you have to do is remember the quadrant angles, 0, 90 degrees, 180 degrees, except in radian measure. So it always counts by pi over 2. So 1/2 of pi, and then a full pi, and then 1.5 of pi, and then 2 pi. The y-coordinates, though, the output values of these points are the ones that you really need to pay attention to, because that's what's going to be different between sine and cosine. So think of the pattern of the wave. Sine starts at its midline and then goes high, back to its midline, then low, and ends at its midline again. As opposed to cosine, which starts high and from there has to go to its midline. If you start out high, there's only one place to go. After its midline, it goes down, back to its midline, and back up. So the 5-point summary for cosine is, well, the same 5 angles, but the output values are going to be different. 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and finally 2 pi, 1. And what we see is the same kind of pattern to the output values here based on what the wave does. Cosine starts high and then transcends downward and then rises back up. And if you have these 5 points, you've established a single period of the sine or cosine function, and you can just extend that pattern over and over and over again to each side. Now, how many times? Well, most problems will say something like, graph 2 full periods of the function or something like that. Or even if it doesn't say that, if it's got a preset grid, it'll want you to draw it all the way to each end of the grid, as far to the left and as far to the right as the grid goes. So every problem is different. But these are the 5-point summaries. So we can use those to actually do some sine and cosine functions. So let's try one. Here's an example function. F of x equals 3 sine of 2x minus 1. So we've got several operations being introduced in addition to the sine function. But at least the sine function tells us what our 5-point summary should be to start. So I'm going to start out by listing out those points here. 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, and 2 pi, 0. These are the 5 points for the sine function unaltered. Now it's our job to go through and start talking about the different operations that are introduced here and what transformations they cause. And part of that is we got to follow the order of operations. So our first thing that we would do here is start inside where the x is, where we have a multiplication by 2. That will cause a horizontal distortion. That's going to stretch out or compress the wave from side to side. That should affect the period then? The period normally would be 2 pi. However, a horizontal distortion is supposed to divide all of the x stuff by that value. So the period would normally be 2 pi, but it's going to be divided by that 2. And as a result, we're going to have a different length period, something that is stretched out or compressed. In this case, compressed. The period now is going to be pi because of the horizontal distortion. Now, back in the earlier part of the semester, when we talked about transformations, what we would have to do is actually take every one of these points and take the x value and divide it by 2 and get a new ordered pair. 0 divided by 2 is 0. The y-coordinate is unaffected. Pi over 2 divided by 2 is pi over 4. The y value is unaffected. Pi divided by 2 is, well, pi over 2. 3 pi over 2 divided by 2 is 3 pi over 4. And again, none of these y values are being affected. 2 pi over 2 is pi. Well, we know that because we did 2 pi over 2 up here where we got the period. And that's kind of an interesting thing to realize. Each of these points, if you look at the angles, the input values, they're evenly spaced. They're all evenly spaced angles. If we compress the distance between them, they're still evenly spaced. So if I might suggest, rather than going down the line and doing pi over 2 divided by 2 and 3 pi over 2 divided by 2, here's another interesting way to do this. I'll fill in the y values afterward, but here's an interesting thing. First of all, an x-coordinate of 0 is going to be unaffected by any divisions. So it's still going to be 0. A stretch or compression is going to affect the further out you are, the greater the effect is going to be. So in the dead center at x equals 0, there's no effect from the distortion. What I'm going to do then is I'm actually going to skip down to the bottom. And that x-coordinate would have to be pi. How do I know that? Because that's the period. Instead of 0 to 2 pi, I now have to do the whole thing in a distance of 0 to pi. So I now know where the end of the period is based on the fact that it starts at 0 and it's got to take a distance of pi to run through its entire cycle. As for the other points, they're all subdivisions in between these. I have to split this into 4 equally spaced sections. Probably the easiest way to do that is to start in the middle and say, well, what's halfway between 0 and pi? Pi over 2, of course. And then for each of the other 2 points, it's halfway in between the others. Like here, this point has got to be exactly halfway between 0 and pi over 2. And that has to be pi over 4. So they're all evenly spaced. 0 to pi over 4, and then pi over 4 to pi over 2, And then from pi over 2, the next even spacing would be 3 pi over 4. So you can divide each of the x values by 2, but if you know the length of the period, you know the beginning and end, all you have to do is evenly space the other ones in between. The y-coordinates here are unaffected because we're doing a horizontal transformation. Okay. There is no addition or subtraction inside with the x, so that rules out horizontal shifts. The sine operation is the next operation that happens after that times 2. That's the basic operation, so we can skip over that. The next operation is a multiplication by 3 out in front of the whole thing. That is going to be a vertical distortion. Again, it's not negative, so we have no reflection. It is a vertical distortion. It is going to multiply every y value by 3. What that means is that when the wave rises above or dips below, it's going to go 3 times higher and 3 times lower. That is going to affect the amplitude. The amplitude is that value of 3 because we have a vertical distortion by a factor of 3. It causes the wave to rise higher above its midline and fall lower below its midline than it otherwise would do. So, we are going to take each y value and multiply it by 3. Well, I suppose we could do that, and the y values are nice. They're zeros, ones, and negative ones, so they're pretty easy to work with. I tend to like to think of it like this, though. Zero, zero, because, well, a y-coordinate of 0 is unaffected. This is the amplitude. It should not affect where the midline is. It should only affect the points that rise above it and below it. So if we keep to this pattern of the y values, the pattern of the sine wave, we start at the midline, and then in the next point, we go above the midline. Except instead of 1 above it, now we have to go 3 above it, because that's the amplitude. Then we go back to the midline. Then we go below the midline, but 3 spaces below it instead of 1. And then we end back at the midline. That leaves one more transformation, one more operation, the -1. That subtraction occurs after the sine operation, which makes this a vertical shift. A vertical shift is going to affect where the midline is, because the entire wave is going to get picked up and slid upward or downward, depending on whether it's positive or negative. In this case, downward one. The entire wave is just going to be picked up and moved, slid upward, in this case down 1 space. That is going to affect the midline, because the midline is the position of the wave. It's that central position. The midline is now going to be y equals -1 instead of y equals +1. So, we can again take every y value and add -1 to it, or subtract 1 if you will. Or we can just use the position of the midline, -1, and then 3 spaces above it or 3 spaces below it as the pattern goes. So our midline is now -1. Then we go 3 spaces above that, which would peak us out at 2. And then back to our midline, -1. And then 3 spaces below it, 3 spaces below it, and then back to our midline. Now, that accounts for all of the operations and therefore all of the transformations. That means that these points here are the 5-point summary for our transformed function, which means we can plot those points and get the appearance of this wave. Now, here's the interesting part. You'll notice I did not put any scale on these axes. And the reason is I didn't know what scale I would need when I started this problem. Now that I've done all the transformations, I do know the scale I need. That is to say, I want to be able to find the x-coordinates of pi over 4 and pi over 2 and 3 pi over 4. So those are all spaced out by pi over 4. So I should probably have my tick marks spaced out by pi over 4. So pi over 4, and then 2 pi over 4, or pi over 2, and then 3 pi over 4, and then 4 pi over 4, or just pi. Okay, well that gets a little ridiculous, so I'm going to make it a little bit nicer and just do every other tick mark I'm going to label. I'm also going to label them on the other side because, well, the wave does extend both directions. Now, as far as the y-axis goes, again, I can see the y values that I need, -1, 2, -1, -4, and -1. So, I pre-drew the axes. If you're drawing your own axes, you can set it up so that you can have the y scale count by ones, which is probably the nicest way to do it. In this case, since I have to work with what I've got here, I can't get down far enough to have each tick mark count as a whole number. I'll never get to -4. So I'm going to count by twos. -2, -4, +2, +4. And that way I can still hit the ones, the -1s in between because I've still got that space in between there. So now I'm ready to plot my points. 0, -1. Pi over 4, 2. Now, because I set up my scale the way I did, all I have to do is move over 1 tick mark to the right and go up to 2. 1 tick mark to the right and back to my midline of -1. 1 tick mark to the right and down 3 spaces to my bottoming out at -4. 1 tick mark to the right and I'm back at my midline. And here we go. One cycle of our wave. And all we have to do to see the rest of it is just extend the pattern. From my midline, go up, back to my midline, down, back to my midline. And the same thing in the other direction. Just have to make sure to follow the pattern backwards. If I just came down, going from right to left, then I have to go the rest of the way down to the bottom, back to the midline, up, midline, down, midline, up, etc. And there is my function. Now, it looks basically exactly like we had on the other, on the original sine function when we did that. So, I mean, it's hard to see the transformation if we're adapting the scale to fit our points. So I'm going to draw in here the original sine function. Let me pick a color it's a little bit more visible than that. I'm going to draw in here the sine function using its original points so we can see the comparison. The original sine function would start at 0, 0, and then go to pi over 2, comma 1, and then pi, comma 0, 3 pi over 2, comma negative 1, and then 2 pi, comma 0. So the original sine function, for comparison's sake, would look like this. So in that way, you can see the horizontal compression. You can see how the wave was jammed together side to side to fit more cycles in the same amount of time. You can also see the greater amplitude because this wave has a much higher rise and fall than the original sine. And you can even see the difference in the midline because it's centered lower than the original sine function. So, I mean, it's not necessary to draw in the original sine, but I think it's helpful to do it for a comparison. All right, so a brief review here. We followed through the order of operations and pegged which transformation it signified, which of the characteristics of the wave was affected by it, and we made it happen on each of the points. Either by performing the arithmetic as we saw earlier in the semester, or by using the things that are unique to a periodic function such as the sine function, namely the even spacing of the points in their x-coordinates and the pattern of the y-coordinates, starting at the midline, then going up, and then back to the midline, then down, then back to the midline. So whichever way you want to address this, the nice thing about the sine and cosine functions is they do have those patterns. They do have these characteristics of period, amplitude, midline, which give us another way to deal with the transformations rather than doing this arithmetic on every single point. So let's try it out on the next function. The next problem has f of x equals cosine of 3x minus pi over 2 plus 2. Okay. Well, different stuff, that's all. Just different stuff. All right, so we've got our operations in here. The cosine is the basic function operation, and we've got several other things occurring. First up is this multiplication by 3. Second up is this subtraction of pi over 2. Then the cosine occurs, and then this plus 2 at the end. So we again have 3 transformations here. First off is that multiplication by 3 in there. Now, since that happens before the cosine, that is a horizontal distortion. And yes, it is a multiplication by 3, but horizontal tends to work in an inverse relationship, so it will divide by 3. Now, what that means for the period is, again, we take the original period of the cosine function, which is 2 pi, and now we're going to have to divide it by 3. And, well, that doesn't simplify, so we just have 2 pi over 3. Okay, not the nicest period, but certainly we can work with it. All right, so let's take a look at the 5-point summary here. Remember, this is cosine, and cosine starts high, then goes down to its midline, then drops below, then back to its midline, and then it ends back high again. All right, so what we have here now is we can, again, actually do the x divided by 3, or we can use the periodic nature of the function and the even spacing of the points. Now, again, 0 is always going to be unaffected by a distortion, and therefore we know exactly where it's going to end up, because it has to take a distance of 2 pi over 3 from beginning to end. The rest of it then is splitting the difference to get halfway in between them. So halfway in between 0 and 2 pi over 3 should be 1 pi over 3. And then halfway between 0 and pi over 3 is pi over 6. We now know the spacing from 0 to pi over 6 is pi over 6. And then another pi over 6. And then another pi over 6 would make it 3 pi over 6, or pi over 2. So again, probably nicer than actually dividing these fractions of pi by 3 and having to do it 5 times, is if you can work out the spacing, the even spacing, it really is a lot faster to fill in those points. Okay, next up is the tricky one. That minus pi over 2 signifies a horizontal shift, but we have to also take into account the distortion. See, normally the shift might be a distance of pi over 2, but that distortion has altered everything horizontally. So that's why when we find the horizontal shift, sometimes called a phase shift when we're talking about a wave, in order to find it, we actually have to take the 3x minus pi over 2, set it equal to 0, and solve. So we add pi over 2 to both sides, and then divide both sides by 3. That is the amount of the shift. The shift is right pi over 6. So we actually have to take our x values and add pi over 6 to them, which actually isn't as bad as it might sound, because they're already spaced out by a distance of pi over 6. So we're not going to start at 0 anymore. When we shift over, 0 plus pi over 6 is, of course, pi over 6. Now, to go a distance of pi over 6 again, well, actually, we kind of already have that spacing in the points over here. They already go up by pi over 6, so we can just kind of follow the same pattern. After pi over 6 should be pi over 3, and then pi over 2, and then 2 pi over 3, and then another pi over 6 after that would make it 5 pi over 6. So again, we're just using the even using the even spacing, we know that each of the points is pi over 6 apart, and we're shifting over pi over 6. So, not a big deal. Lastly is that plus 2, which, as we've already seen, is a vertical shift. That's going to affect the midline. So we can, again, add 2 to each y value, and thank God we're done messing with those x values now. The y values are easy to work with because they're all zeros and positives or negative ones. But again, if we do this in terms of thinking of the midline and above it or below it, we start out 1 above the midline because there's no change to the amplitude here. So we start out 1 above the midline. Then we go to the midline. One below the midline. Back to the midline. And we finish up 1 above the midline. And those are our points. So again, we can write the scale on the axes accordingly. All of the x values are spaced out by pi over 6, so that would seem to be a good spacing to use. So 6 tick marks to get us to pi. I'm just going to mark a few in between. And then the same on the other side. As for the y-axis, the only y values we see are 1, 2, or 3. So unlike the previous example, I did set this grid up appropriately for that. I kind of stole from the idea that I knew where this was going to go, so I just set it up to work nicely. So all we got to do now is plot our points. Remember, we're not starting at x equals 0. We're shifted over, so we're starting at pi over 6. Down to the midline, below the midline, back up, and up top. Again, there's our kind of V shape, rounded off, I guess, more of a U shape perhaps. And all we have to do now is extend the pattern. Back to the midline, down low. On the other side, down to the midline, we go below it, back to the midline, up above. Back to the midline, down below, back to the midline, up above. And there is our sine curve, or cosine curve, cosine. Now, an interesting thing happened here. We actually shifted what turned out to be a quarter period to the right. And look at how it goes. If you look at it from the point of view of this, it actually now starts like sine does if you look at it in terms of starting from 0. So it's kind of interesting, again, that sine functions and cosine functions are just slightly out of phase with each other, hence the phase shift. They're just slightly offset from each other. If you shift horizontally just a little bit, you can actually turn a cosine function into something like a sine function. That is to say, if we did the same function, the same horizontal distortion, the same vertical shift, but we left out the horizontal shift and used sine, we get the same function. That is to say, this function is the same as if we did sine of 3x plus 2. So if we switch to sine and leave off that horizontal shift, now, the only reason that works so cleanly is because the horizontal shift was a quarter period, and that's the exact amount that sine and cosine are off by, so it's not like we can do this all the time. But my point is that we can adjust this to make it into a sine function. Any sine function can be written as a cosine, and any cosine function can be written as a sine function. If they have the right horizontal shift, they can be turned into each other. Now, like before, I think it's often helpful to look at the original function to get a feel for what we're dealing with here. The original cosine function would start at 1, and then by the time we hit pi over 2, would be at its midline, and then at pi would be back to its, or would be down below its midline to its lowest point. The graph goes beyond, the period goes beyond what we can see on the graph here, so I'm actually going to go back the other direction. That would be a single period of the original cosine function unaltered. So you can see again how the horizontal distortion has compressed this wave so that it goes through its period more often in the same period of time. We can also very clearly see the vertical shift happening, the new midline, and even the higher frequency, the shorter period makes it a little bit tougher to see this. But if you look at it, you can see again the phase shift happening there because the original cosine starts at its high point here, whereas the transformed function starts at its high point a little bit off to the side. All right, let's take a look at one more. A nice simple one, because really I just want you to see something that can happen here. We get so used to the x-coordinates always being weird fractions of pi, but it all depends on how the function works. It all depends on what the things are. Sometimes you have a distortion that is in terms of pi. That's what's happening here. The first operation in this is the multiplication by pi. That's going to cause, again, a horizontal distortion. And what it's going to do is it's going to cause us to take every x value and divide it by pi, and that includes the period. The period is normally 2 pi, and now it's going to be divided by pi. The pi's cancel out, and that leaves us with a period of 2. That's significant because the 5-point summary normally would have fractions of pi for its x-coordinates. But if we do what we did in the previous 2 examples, x divided by pi, or rather, if we evenly space everything, we know that this is going to start at 0, and if the period is 2, that means it has to end at 2. Well, that's kind of nice because that's much easier to work with than fractions of pi. It's actually an integer. Halfway in between 0 and 2 is 1. That's the middle of the period. And then for the other 2 points, what's halfway between 0 and 1? 1/2, of course. What's halfway between 1 and 2? 1 1/2, of course, or 3/2. That happens sometimes. If the horizontal distortion is based on pi, then it can cancel out the pi that's in the period and leave you with x values that are as nice to work with as the y values. That can happen. Again, there's only one other operation in here, and that's the times -1 that's in front of this whole thing. That causes a vertical reflection. Now, we haven't seen a vertical reflection in the previous examples, and to be honest, what we're going to see here is that a vertical reflection of a wave doesn't seem to have terribly much of an effect. Now, an interesting thing is that doesn't actually affect the amplitude. The amplitude is still 1, but it does affect the order of the wave. That is to say, sine normally starts at its midline and then goes up. The vertical reflection is going to cause this to actually go the other way. And while we may start at the midline still, instead of going up, we're now going to go down first, then back to the midline, and now up, and then back to the midline to finish it out. So again, the amplitude is still 1. We still only go 1 space up and 1 space down, but we do it in the opposite order now. So, again, we get to address our scale here. Since our points are spaced by halves, we should probably have our tick marks spaced by halves. For the vertical axis, well, again, nothing's really changed. We're just doing it in the opposite order, so it should work just fine if we use 1 and -1. And then it's just a matter of plotting those points. 0, 0, and then down to -1, back to the midline, up to 1, back to the midline. So it is a vertical reflection of the sine function. Yes, because instead of going up first and then down, it goes down first and then up. And then, of course, we can extend that in each direction as far as we need to, as far as the grid will allow. Now, in the previous two examples, I ended up drawing the original unaltered function for comparison. That's going to be a lot harder to do here because the scale of the x-axis for the original is based on pi's, and for the transformed function, it's not. So that would become very difficult to show. That being said, we can just use some decimal equivalents, and one of the easiest is pi because its value is pretty well known. It's about 3.14. So the original sine function would have its half period about here, which means it would have to start at 0 and go up and then down to by the time you hit pi. So again, we can see the distortion here, and again, the vertical reflection is a bit more apparent because we start out by going down instead of up. But again, we can see the horizontal distortion in effect here. Again, it's not necessary to draw the original unaltered sine function in there, but I think, again, it can help to understand how the transformations make this different, because when we adjust the scale to fit our transformed function, we end up with a wave that looks very, very much the same every single time. The only difference is the scale on the axes. So that's sine and cosine functions. That's transformations of them. Again, we're using the same transformation kind of thing that we learned about earlier in the semester. It's just now we're adding in this new information such as period and amplitude and midline, and that can give us another way to fill in those ordered pairs. You can, of course, always do the arithmetic just as we did earlier in the semester, but we have new functions with new characteristics and new sets of points, the 5-point summaries for each. It's just a matter of interpreting the transformations and making them happen on the 5-point summary, just as we did earlier in the semester. Nothing different here, just a different style of function, that's all.